properties of kinetic energy. Okay. And the first thing that we want to go after is definitely this. It's people's language becomes very, very, very sloppy. And so what I want to do is I want to try to correct some of that sloppiness. Only changes in kinetic energy are meaningful. What do I mean by that? Well, according to the work energy theorem, this is how we define kinetic energy. This is the definition. So this word here is meaningful. But if I look at the kinetic energy at a single point, it is meaningless. It has nothing. So if I write kinetic energy like this is meaningless. It means nothing. So it's that delta symbol that's meaningful. Okay, it's that delta symbol that's meaningful. So here we go. So what we know here is that kinetic energy depends on speed and work. And you know this. You absolutely know this. You are an expert at this. We're just trying to put it into the language of physics. So here we go. So what I want to do here is that I want to start off with speed dependence. So when I look at speed dependence, what we want to do here is that we want to compare two situations and ask which requires more work. So what we're going to do here is that we're going to compare two situations and ask which requires more work to stop. So here we go. Let's set the situation up here. So what we're going to do here is I need two cars. Okay, so I'm imagining there's this car. And we'll continue with our light blue car. And then what we're going to do here is that we want to draw a second car and compare these situations. So if I look at this thing here, how about if I copy this? But this time, I don't want a baby blue car. I want something different so that it's easier to identify. How about if we make this a red car? And what we're going to do here is that we want to compare kinetic work to stop. So there's this car that's traveling this fast. And then I have the red car, which is traveling faster. So which one is harder to stop? Of course, the red car is harder to stop. You already knew that. It's moving faster. So what do I mean by work? Work tells me that this car has a smaller kinetic energy to start off with, whereas this car has a higher kinetic energy. Now remember, if you say kinetic energy, this is what that means. Remember, kinetic energy at one point is meaningless. work is meaningful when we change the kinetic energy. So that means here is that what we got to do here is that we got to come in and what do we got to do? We have to stop these cars. We have to stop these cars. That's what we got to do. So that means I got to stop the blue car. I got to stop the red car. So that means when I look at this thing, I know that this kinetic energy is zero. I know that this kinetic energy is zero. So now we're talking about change. So that means we brought this to rest. We brought this to rest. Then we ask the question, which requires more work? So immediately what we say here is that we can see that there's less change in energy in the blue car. So when I look at this guy, I look at this guy and I go, oh yeah, there's less change in kinetic energy here. And if I look at this other car, this has a bigger change in kinetic energy, right? So when I come in here and I do this, we know that this has smaller changes in kinetic energy here, bigger changes in kinetic energy. So immediately what we're saying here is that the work has to be bigger here because it took more to stop it, whereas this one has smaller amount of work. Now question, why was the car, the red car, harder to stop? Why was the blue car easier to stop? So now I use my equation. Remember my equation? It's 1/2 mv squared for the velocity, for the kinetic energy. So when I look at this less work, it goes like this. Oops, that's not what I wanted. It goes like this. Both cars have the same mass. The difference is this is v squared like that. That v squared is big. So why was the kinetic energy so big? Because the speed was higher in the red car. So when I go and I look at these guys, I know that they're both zero. And then we could say, that's the reason why. So we knew that this guy was going to do what? This required more work to stop. Why? Because it had a higher speed. This guy here had less work to stop. So instead of saying work, we're saying change in kinetic energy, right? Change in kinetic energy. So if I was to draw this bar, here's what we find. I look at the blue car and I got to talk about work. So the blue car had what? It had less work. So I come over here and I go, okay, this is how much work the work was. But the car though started off with what? Zero, with zero kinetic energy. And so what did I do? Well, I did that. And since the work cannot disappear, it has to reappear. You could see that the final kinetic energy of the blue car is going to be this big. Look at the work. It does not disappear. But now if I look at the red car, if I compare these guys, the red car has this amount of work. Nope, 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 nope. It has more work, right? There's more work in the red car. As a consequence, when I look at the kinetic energy, it started off from rest, but then it went to this higher kinetic energy. So when I compare these situations, what are we seeing here? That the kinetic energy is higher for the red car because there was more work done. The kinetic energy is smaller for the blue car because there was less work done. Again, there's a change in language. We say what? Small work. To stop a car. Therefore, we had a smaller change in kinetic energy. So in this case, this change looks like this. Maybe I should have done, yep. Just to be color coded, make sure that I'm trying to. Whereas now I have what? I have large work to stop a car. So therefore, this is now going to be a larger change in kinetic energy. That's what that bar diagram is telling us. Again, you know this. Let's go to the mass. If I go to the mass dependence, again, you know all about this. You have intuition, and we want to keep using this. So in this case, what are we going to do? We got to compare two situations again. So what I'm going to do here is that I'm going to focus here. I'm going to take this situation right here. Since we already did this, I'm going to go look at this guy right here. So I have my car situation. And when I look at my car, I'm going to say that the mass on this guy is smaller. Okay, so this guy has what? Has a smaller mass. But what I'm going to do this time is that I'm going to make the speeds of these to be exactly the same. So now I have the same situation, but now I have a big truck. And so when you look at this truck, you can clearly see that this truck has what? Has a much larger mass, right? But the big difference here is that this guy's going to be going the same speed. So the question is, what do I got to do? Well, in each of these situations, I have to do what? I have to stop these cars. So eventually, I got to do what? I have to bring this to a stop. Right? I have to bring this to a stop. And so what you're seeing here is that now this speed is 0 and this speed is 0. So who or what car is going to be harder to stop? Remember, they're driving the same speed. So if they're driving the same speed, we have to agree that this is going to be harder to stop. So when I look at the change in kinetic energy, that has to be bigger. So then we play the same game that we did before. Well, this change in kinetic energy is smaller. This change in kinetic energy is bigger. So the question is, why are they bigger? And the reason why they're bigger here is that when you look, while the speed is the same in both cases, the big difference is the masses. This one has a big mass, and once you get it moving, it has to be harder to stop. So when I look at this is the reason why this kinetic energy here is small. And this is the reason why this kinetic energy is so big. But that just means what? That this was a smaller work. This was a bigger work. That's what that means here. So the reason why this took so much work here is that you had a larger mass truck requires more work to stop. So instead of saying work, we say kinetic energy. Okay, whereas in this case here, we say that this is a smaller mass. And then just following our thinking here, this is less work to stop. Okay, less work to stop. So I want to leave kinetic energy, but I want to do this last piece before we go. So I have a question that I want to answer. And this is what the question is. Which requires more work to stop a bowling ball or a baseball with the same kinetic energy? Which one would have more work to stop? The bowling ball or the baseball with the same kinetic energy? Well, what we know here is that from the work energy theorem, that implies that if the kinetic energy is the same, then they must have exactly the same amount of work. So this implies here is that same change in kinetic energy implies the same work to stop. Right? Because that's what kinetic energy means. So then when I look at this thing, they then have the same. So that means here that the kinetic energy of the bowling ball must equal the change in kinetic energy of the baseball. And that has to have the exact same work according to them. So the question is, how can this be? And what we note here is that when I look at the change in kinetic energy of the bowling ball, well, what do I know about the change in kinetic energy of the bowling ball versus the change in kinetic energy of the baseball? So in each situation, what we're going to have here is that we have to stop them, right? So this implies that we must stop. So then what's different about these? Well, what we know here is that the mass of the bowling ball is larger while the mass of the baseball has to be small. The only way this could be true here is that the only way these guys could be the same if the bowling ball is moving slower and the baseball is moving faster. That's the only way this must be the case. So what we're seeing here is that we then say is that the bowling ball must be moving slower. Whereas in this case, what we're seeing here is that the baseball must be moving faster, right? It must be moving faster. And so, so if we were to look at a picture here, it's really something like this here, right? So I have a big fat bowling ball, right? So this is my red bowling ball. And because this bowling ball has such a big mass, it's moving really slow. But if I look at the baseball, well, as I throw this baseball, what you're seeing here is in this case, it has a little mass, but it must have what? A high speed. These two guys, oh, I didn't finish I ran out of space here. I need to move this over. So picture-wise, it has to look like this here. What do I got to do to the bowling ball? I got to bring it to rest. I got to bring it to rest. What do I got to do to the baseball? I got to bring it to rest. Right? I got to bring it to rest. So in this case, this is what this picture actually means. That's what we mean by the change in kinetic energy.